Okay, so my name is Paul Kondratyev. I'm with the Tescom Precision Fluid Control brand of Emerson. And today I'm very excited to present to you about helping hydrogen refueling stations tackle pressure management challenges. So big thank you to SAE for hosting. Now you may be asking, I guess, what makes you qualified, or I guess, what do you know about refueling stations? And my role at Emerson is in product marketing, and I basically focus on making sure that I hear our customers' pain points and issues and translate those into solutions along with our engineering team. And so over the past couple of years that I've been in this role, I've gotten to work very closely with a number of refueling station manufacturers globally and hear out their issues. And these are some insights that I've gathered that I'd love to share with you guys today, with the hopes of giving you a little bit of insight into the challenges and solutions of hydrogen refueling. So although I'll be focusing on refueling, I'd like to also point out that these challenges apply across the hydrogen value chain, from generation with, if we're talking green hydrogen, electrolysis through renewable energy, all the way to end use and mobility. Anywhere you have compressed hydrogen, and I'll be focusing on gaseous hydrogen only, although liquid hydrogen, as the previous presenter mentioned, is also something that shows promise. But I'll focus on the gaseous side, which is a little bit more mature of a technology. So the insights I'll be sharing with you will be relevant throughout the value chain. But I'll focus on mobility. And one question I'd like to start with is, just ask yourself this question: what do you think is the number one thing that station manufacturers can do to ensure that they're successful, that hydrogen as an alternative fuel is successful? And to me, the answer to that is providing the same user experience as traditional refueling. And the reason for that is, I think the only way that hydrogen can be the choice of alternative fuel ahead of battery electric is in those use cases where users really do not want to wait as long as batteries need to charge, and are really seeing the value of hydrogen over battery electric, and seeing it as a cleaner alternative to traditional fueling. And so 4 considerations that I will speak about today from a station design perspective that allow this similar user experience to traditional refueling. And those 4 are safety, performance, reliability, and speed. Okay, so let's dive into the first one with safety. And I know talk of the Hindenburg and safety with hydrogen is often a touchy subject. And I want to echo the previous sentiment, of the sentiment of the previous presenter, that hydrogen does present certain safety challenges. However, those are manageable. And so I'd like to speak to those challenges a little bit here with regards to gaseous hydrogen. First and foremost, hydrogen being a tiny molecule, it is very prone to leakage, right? So here on the left-hand side, I've got some just general molecular radii or diameters to compare the molecules against each other. And you can see with its tiny size, no matter how good your seal is, eventually, as it starts to wear and tear, you're going to get some small amount of leakage. And so that's the first factor in considerations of hydrogen safety. Now, that first factor means nothing if you don't have the other 2 in mind. Low ignition energy and wide flammability range mean that whenever you do get that little leak of hydrogen, once it accumulates to about 5% or greater percentage of volume in air or oxygen, it becomes prone to ignition with very, very little ignition energy from any spark or ignition source that you have in the system. And so that's what, as a component manufacturer for valves and regulators, that's what Tescom provides for refueling stations. We try to eliminate any or control any hydrogen leakage and eliminate ignition sources. And one example how we do that in a pressure regulator, here we have a cutaway on the right-hand side, is if you look at the white triangles, those represent the sealing points in the system. And if you follow the outlet pressure, the blue outlet pressure here, these seals are eventually going to have some sort of leakage when you use these regulators over and over. And so what we'd like to do is we like to capture that leakage with the yellow area. I can't see my own mouse, but the yellow area in the cutaway represents that captured leak port. That means that the leakage never leaves the system, but rather is captured and vented away to a safe location in a safe manner. So you never have hydrogen accumulating within your dispenser or some other system. So that's safety. Moving on now to performance. And this is to me, a very interesting topic. So on the left-hand side, what you have here is a representation of a hydrogen dispensing event per the SAE J2601 fueling protocol, and there's other protocols in development, but the concept stays the same. The station needs to make sure that the pressure is ramped from lower pressure to higher pressure during the fill, and what you get is this increase in temperature. And there's two reasons for that. Number one, negative Joule-Thomson effect of hydrogen. When it expands, it heats up, unlike other gases. And second, you're jamming this pressure into a finite storage, you're going to get some heat generated. And so in order to stay below the temperature limit of the vehicle tank and not overheated, the pressure ramp rate has to be controlled carefully as to not fuel too quickly. You also don't want to go too slow, or the user will have a poor experience. Therefore, stations are relying on pressure regulators controlled by PID controllers, such as here in this case, a TESCOM pressure regulator with the ER5000 electropneumatic regulator that takes in a pressure set point from the PLC or whatever controller that sends that pressure set point, and the controller is able to compare the pressure downstream at P2 to the set point and adjust accordingly to where you can follow that ramp rate live and adjust it as needed based on the operating conditions of the system. And so this is a very important, the reason this is important to the user experience is that if you overheat your vehicle tank, you're going to have to stop the fuel. And as the user, you won't be very happy. You expect the same thing you get at a gas station, right? You come in, you fuel, and you're successful every time. And so technology such as this PID controller regulator combination is key to allowing stations get that repeatable success. Number 3, maintenance and reliability, huge. So one of the standards that we like to refer to in hydrogen refueling for valves and regulators is the ISO 19880-3 standard. And it gives us an idea of what we can expect from this harsh environment of hydrogen. And why it's harsh is the high pressures, obviously 15,000 PSI is often the upper pressure limit in a refueling station. When that's cycled back and forth on a valve, especially at cold temperature, the elastomers get really beat up. And so the guidance per the standard is to replace the soft goods 16,000 cycles, which, just doing some estimating, 50 fueling events per day gives you about 6 months of operation. So what we like to do is we like to provide the station operator the easiest maintenance as possible. So with the TESCOM VA series valve, you can see here the bonnet is easily removable and replaced with a cartridge swap that allows for fast maintenance. And even in general, obviously, number one goal is reliability and station uptime. And so the best way that we can help the station continue to operate without any extra downtime is by using our technology that we know works better than competition in terms of the travel that the valve has to do compared to a diaphragm valve, a bellows valve, or a ball valve. And so that's something that we know is of value to station operators. So that's reliability. All right, moving on to our last one here, speed. And so when first stations were being developed in, let's say, the 2000s, early 2000s, right, they were kind of more proof of concept. And a lot of these stations just focused on getting the fuel operation done. And so they would fuel let's say, a Toyota Mirai with a 6 kilo tank in 5 minutes, that's about 60 grams per second flow. And as the technology is becoming more mature, we're recognizing that hydrogen as an alternative fuel is most valuable to these heavy duty vehicles, either, semi trucks, class 7, or off-road vehicles, stuff like that. And so now you're looking at fueling a 100 kilogram tank, and you want to stay reasonable in your user experience so that these long haul companies, they choose hydrogen vehicles over battery electric. So that puts some restrictions on the designers of the station. Now you've got to fuel a 100 kilogram tank in 10 minutes, which gives you a much higher flow rate, almost 5 times what you've had in the past. And so the way that you can achieve that is you really have 2 levers as the station manufacturer. You can either increase your pressure drop, right? Because if your high pressure storage that's fueling using that protocol, if you remember the ramp rate, that's fueling the lower pressure vehicle tank, well, you can either increase your delta pressure, the difference of the pressure of the storage tank in the priority panel and the vehicle tank, which allows you to fuel more hydrogen per minute, or you can increase the component size. And here on the right hand side, as a reference, there's some estimate numbers for a 170 grams per second flow rate, which is on average what you need to fuel 100 kilograms of hydrogen in 10 minutes. You can achieve that with either increasing your pressure drop, as you can see here, from 60 to 371, or increasing your CV, or your rating of flow capacity. So that's another key consideration for hydrogen refueling stations as they design new systems going forward. Okay, so, we obviously talked about safety, performance, reliability, and speed. And those are 4 key concepts of pressure management, right? But there's a lot of other things that have to happen within the station. And one of the key considerations that I'd like to share outside experts who have experience in that technology in different industries, possibly outside of hydrogen. And so here at Emerson, we're lucky enough to have a collection of brands that can solve these issues, from PLC and data visualization software expertise to flow meters, pressure measurement, all across the board. And as I go into the next slide, even going outside of just pure refueling, like I mentioned at the beginning, these are challenges and considerations that are relevant across the whole hydrogen value chain. And as we continue growing as an industry, these issues are going to need to continue being solved. And we're lucky enough to have a good amount of expertise in the field, and we always welcome any new feedback or opportunities for learning or development, especially myself in my role. So if you find any of these concepts or products or challenges I've described interesting or relevant to what you're working on, please feel free to reach out at any point. I think my information will be shared, LinkedIn, email, whatever it is. So yeah, very, very happy to be a part of this and just share my 2 cents on challenges of refueling stations with regards to pressure management. And with that, I think we have a couple minutes for questions if there are any.